uniform bar of mass m is 2.5 kilograms and length L of 2 meters is supported in static equilibrium in a horizontal position by a pin at its left edge attached to the wall and a string attached to the right edge, which makes an angle relative to the bar of 35 degrees. The first characteristic we notice in this problem is that all objects are motionless, thereby identifying this as an equilibrium problem. An equilibrium problem is a force problem, and the first step in every force problem is to draw a free body diagram. We will draw a free body diagram for the flagpole itself, since this is the object in the diagram that receives the greatest variety of forces. The first force that we consider is gravity acting on the flagpole. Gravity acts at the center of the pole and is of an amount m times g. The next force that we see is the tension force. Tensions always pull, and they're always directed along the string or wire. Finally, we need to consider the effect of the pin at the wall. This is not what we consider a surface or contact force, because we're going to rely on more than friction to hold up the left-hand edge of the bar. We have it actually bolted using a pin. This means that the wall can apply a strong force in any direction. It is typical in a problem like this to still consider that force as having two components. One of them we call normal along the bar itself, and the other one we're going to call upward, since obviously if we push down on this end of the bar it would go down and we need to hold it up. This free body diagram is of two dimensions, x and y, and although we don't have an acceleration to guide us in selecting the plus direction, we can see that the resulting equations will be easiest if we make a coordinate system that is horizontal and vertical. This is because 3 of the 4 forces are already directed along the horizontal and the vertical. The tension force is the only one not compliant with our coordinate system, and so we'll break it into 2 components before we proceed with the rest of the problem. This is the horizontal component, and that's the vertical component. Recognizing that the angle of 35 degrees is in this corner, we note that this component is opposite to the 35 degrees and is therefore tension times the sine of 35. And this component is adjacent to the 35 degrees, therefore of an amount tension times the cosine of 35. Despite the fact that students will most often begin an equilibrium problem by analyzing the Cartesian coordinates, it is often advantageous to begin our analysis of an equilibrium problem using the rotational or torque equation. Let's see why. We recognize that the sum of all forces as well as the sum of all torques will be 0 because the object is motionless. In formulating a torque, since we need a force times radius, we're going to need to identify the pivot point around which the object is not rotating. Since the object is not rotating, any pivot point is a good candidate for formulating the torque equation. We can apply that pivot point with the red dot as shown here, 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 or in fact at any location along our entire problem. Because we have freedom, we can use the freedom to simplify the equations that will result when we analyze the free body diagram. This is the reason why the torque equation is most often simpler than the forced equations, because when we use that freedom, we force it to be simpler. If we locate the dot at the left-hand edge, we will eliminate the normal force and the upward force. If we locate the dot at the right-hand edge, we would eliminate the tension. Since tension is one of the things we want to know, we're going to place this dot at the left-hand edge and use that to define our motion. We will select clockwise as the plus direction. This is an arbitrary choice, and you can still get the correct answer even if you chose counterclockwise. Let's begin. There is one force that leads to a torque in the plus direction, and there is one force that leads to a torque in the minus direction. It's the gravity force that leads to the torque in the plus direction. That force is of an amount 2.5 g, but 2.5 g is merely a force. In order to turn it into a torque, we need to multiply by radius, and since gravity applies at the midpoint of the flagpole, the radius is half the length of the flagpole. The force that contributes a torque in the negative direction is the tension. However, we must be careful with the tension. Any force component that is directed toward or away from the pivot applies no torque whatsoever, because when a force is applied towards or away from the pivot, it does not tend to turn the object either clockwise or counterclockwise. Looking carefully at our diagram, we see that the tension component, T times the cos of 35, is directed toward the pivot and therefore does not contribute in making a torque. We need to only use the useful component, tension times the sine of 35, in formulating our torque. We note, however, that of course tension times sine of 35 is merely a force. It is not yet a torque. It needs to be multiplied by the radius, and since the wire is attached to the far end of the rod, the radius that is appropriate for this is L, and as noted earlier, the sum of the torques is 0. In this equation, we can factor out the L, divide it away, and then we find that we have one and only one unknown, leaving us with the tension being equal to 21.36 newtons. Coincidentally, this is exactly the quantity that was asked for in Part A, and we have been asked neither for the upward nor the normal force, and so this ends the analysis of that free body diagram. Let's read Part B to understand where to proceed next. Part B of the problem tells us that the string breaks and the bar pivots around the pin with no friction. We are then asked what is its angular acceleration alpha just after the string breaks. Here's a copy of the free body diagram from Part A, and what we notice is that it's a reasonably correct free body diagram, except that this diagram still contains the tension in the string. And if the string is broken, that force isn't there. So let's remove it from the free body diagram. In this dramatically simplified free body diagram, we recognize that we no longer have equilibrium, since we will only have torques in the clockwise direction. In this case, the pin itself is the pivot point, because the flagpole does indeed rotate around this end. So our analysis will not be sum of the torques is 0, because now the sum of the torques will be I alpha. Let's begin. We call clockwise the plus direction because indeed this is the direction of the angular acceleration. And just as before, we find that the 2.5 kilograms times g is the force that leads to the torque in the plus direction. Once again, we recognize that 2.5 g is not a torque, it's merely a force. We need to multiply it by a radius, distance between the pivot and the application point of the force, and that distance is 0.5 times the length of the flagpole. The sum of the torques is I times alpha, and in order to solve for alpha, which we've been asked for, we need to replace the moment of inertia of this flagpole with some particular form. We recognize that the flagpole is of a shape that is a rod rotating around its end, and we remember that 1/3 mass times length squared is the moment of inertia of a rod rotating around its end. Placing this into the prior equation, we find this result. One of the factors of L will cancel, leaving us with a final expression for the angular acceleration alpha, 3g times 0.5 over the length. Remembering that the length is 2 meters, we get the numerical result, 7.35. Because the prior equation was all in MKS units, we recognize that alpha must also be in MKS units, which for an angular acceleration, the natural units are radians per second squared.